A new passenger train crosses the entire width of Kenya in under 5 hours, running on a continuous concrete elevated structure positioned directly above the heads of migrating elephants and lions. The wild savanna stretches out undisturbed below the massive pylons, while the heavy rumble of the diesel locomotive echoes across the open plains. The contrast is stark. This transportation corridor covers a distance of 500 kilometers between the eastern coast and the inland capital city. The financial scale of this construction reached $3.8 billion. In 2014, that single infrastructure investment accounted for roughly 6% of Kenya's entire gross domestic product, which stood at $61 billion at the time. Every major technical component required for the project was provided by one specific nation. Chinese state contractors held the complete monopoly over the supply of the steel rails, the concrete pillars, and the diesel locomotives operating on the route. Why did Kenya hand over the operational control of its largest infrastructure project to a foreign corporation? The primary cause was the physical breakdown of the older freight transport network. That massive $3.8 billion Chinese infrastructure intervention did not materialize from thin air. It emerged from total physical collapse. The immense Mombasa port continuously processes vital maritime imports for multiple East African nations daily. Landlocked countries like Uganda, Rwanda, and South Sudan depend heavily on this single coastal gateway to survive. The inland transport route was completely broken. Moving those incoming heavy shipping containers inland meant overcoming 500 kilometers of pure logistical paralysis. The original meter gauge railway was physically laid between 1896 and 1901. The narrow tracks were severely degraded. Over 100 years of continuous heavy commercial operation left the British colonial infrastructure fundamentally unsafe. Under the crushing dynamic weight of modern freight trains, ancient metal rails warped violently in the intense savanna heat. The regional delivery schedule collapsed completely. A standard inland cargo trip stretched into a grueling multi-day ordeal through the unforgiving African wilderness. Transporting a single heavy container to Nairobi cost more than shipping goods across entire developed continents. The old railway network failed rapidly. The massive international freight burden shifted entirely to regional asphalt, turning the primary highway into a heavily congested, chaotic transport artery. Endless lines of heavy commercial transport trucks clogged the critical trade route daily. Diesel engines overheated constantly. Broken and abandoned vehicles littered the dusty highway shoulders under the scorching sun. Massive traffic bottlenecks formed instantly. These relentless physical delays completely crippled the import supply chain across the entire eastern region, paralyzing regional economic growth. Abstract economic losses immediately translated into hard physical barriers. Farmers and factory owners watched their profit margins evaporate into completely uncontrollable transportation fees. The century-old British narrow gauge line finally reached its absolute structural breaking point. Freight train derailments became dangerously common. Authorities simply shut down severely damaged track segments, while crumbling steel bridges forced the immediate and permanent closure of emergency rail routes. As collapsing colonial bridges finally choked container delivery from the port, a new financial mechanism appeared in 2014. The Export-Import Bank of China proposed a $3.8 billion loan. The terms dictated a strict financial split. Beijing covered 90% of the total project cost. Kenya carried the remaining 10% liability. This agreement activated the core mechanics of the Belt and Road Initiative. The capital did not simply stay in East Africa. The approved funds flowed directly back into Chinese heavy industries. Building the line required massive material imports. The operation consumed Chinese steel and deployed Chinese heavy engineering machinery. Repayment structures guaranteed long-term economic returns over several decades. To execute this massive transfer of resources, the logistical chain required a unified operator. The China Road and Bridge Corporation absorbed the contract. They secured the complete development cycle, taking full control from initial topographic blueprints to the final track construction. Having secured the financial framework, CRBC engineers initiated a comprehensive satellite scan across 500 kilometers of Kenyan terrain. They deployed drones and aerial laser scanning equipment to map the complex topography of the East African Rift Valley. Every single support column and river crossing required exact load calculations before any excavation could start. The timeline was strict. The contract demanded an operational elevated structure completed in under 3 years. 0 delays allowed. To meet this deadline, specialized logistical networks synchronized the delivery of cement and structural steel across dozens of active construction zones simultaneously. high-capacity excavators, mobile concrete batching plants, and heavy crawler cranes arrived at the sites alongside tens of thousands of workers. The topographic mapping concluded, immediately forcing the engineers to confront the physical reality of constructing a heavy railway directly over unstable African sand. The topographic scans revealed a critical structural vulnerability across hundreds of kilometers of the designated corridor. The trajectory lay directly over loose, unconsolidated sand. Engineers faced a strict physical constraint. A standard track bed placed over this shifting geology cannot support heavy freight traffic. Fully loaded cargo trains generate intense low-frequency vibrations that travel through the rail ties into the earth beneath. Without a massive increase in soil density, these constant vibrations would cause the foundation layers to settle unevenly. Uneven settlement destroys track geometry. It severely damages rolling stock. Before any structural concrete could arrive, the ground itself required total physical modification. Bulldozers first leveled the terrain, erasing local dips and elevations to establish a uniform baseline. Then, specialized water trucks equipped with extended spraying arms moved along the corridor. They saturated the loose sand with precisely calculated volumes of water. This specific moisture level alters the mechanical behavior of the soil. The introduced water creates surface tension between individual grains. Moisture physically forces the loose sand particles to bind tightly together, acting as a temporary adhesive matrix before the heavy machinery arrives. Once the moisture levels registered within the targeted parameters, the construction crews initiated the dynamic compaction phase. Heavy crawler cranes maneuvered into position across the saturated zones. Each crane hoisted a massive solid steel tamper. These dense steel blocks weigh between 10 and 20 tons, equivalent to the mass of several large passenger vehicles combined. The mechanical winch raises the block to a designated drop height of 10 to 15 meters above the surface. The operator disengages the clutch. The steel weight free falls and slams into the wet ground. The collision transfers immense kinetic energy directly into the earth. This high-velocity impact generates a powerful shockwave that propagates downward through the deep layers of sand. The sudden localized pressure violently forces the sand grains into a much tighter structural configuration. It instantly squeezes out the trapped air pockets that normally render loose soil weak and prone to shifting. The crane operator lifts the tamper and drops it again in a strictly calculated grid pattern. They overlap the strike zones to ensure uniform consolidation across the entire width of the future railway bed. Heavy vibratory soil compactors followed the crawler cranes. These massive rolling machines drove back and forth over the strike zones, utilizing sheer static weight and high-frequency internal vibrations to further expel any remaining microscopic air voids. After the initial sand layers achieved the required density, the ground crews spread a thick capping layer of the region's characteristic red soil over the stabilized base. They graded this new material flat and subjected it to another round of heavy vibratory rolling. This intense physical transformation continued sequentially across the flat savanna. The construction crews maintained continuous rotating shifts, executing the compaction grids under ambient daytime temperatures that frequently exceeded 30 degrees Celsius. Surveyors and geotechnical engineers tested the load-bearing capacity and compaction density of every completed segment before authorizing the next phase of construction. The zero-tolerance policy for ground settling dictated this highly methodical pace. Rectifying a foundation failure under a completed operational railway requires completely dismantling the track infrastructure, generating corrective expenses that easily exceed the entire initial construction budget. The newly compacted ground provided a stable platform for heavy rotary drilling rigs to position for the piles. These reinforced shafts plunge up to 30 meters deep, anchoring the rail line directly into solid bedrock. Above the surface, the actual track elevation takes shape. Support columns rise 15 meters high. That vertical scale matches a standard 5-story residential building. 90 tons of reinforced concrete, every 35 meters, for hundreds of kilometers. This continuous material repetition dictates the entire construction schedule. Strict dimensional tolerance remains structurally critical. A single millimeter of misalignment at the foundation stage inevitably multiplies into a major structural flaw at the apex. Surveyors must continually verify the exact coordinates of every single column. This alignment prevents long-term deformation and twisting across the continuous elevated deck. Crews assemble heavy cylindrical steel forms around dense rebar cages. High-strength concrete fills these rigid molds, curing and solidifying steadily under the 30-degree ambient savanna heat. 90-ton pillars, positioned at 35-meter intervals, establish the rigid framework required to support the elevated spans. How do engineers prevent a 100-ton beam from sagging under dynamic railway loads? The solution relies on internal tensioning. High-strength steel cables are stretched tight inside steel molds before the concrete is even poured. Once the mixture hardens, these embedded tendons pull inward. The beam compresses. This locked-in stress grants the concrete the sheer physical resilience needed to endure the heavy, cyclic impact of passing freight trains. Each 30-meter precast girder is manufactured in a dedicated casting yard located near the construction site, ensuring a steady supply of structural components for the advancing railway. Out on the dry plains, the installation process demands continuous mechanized progression. A specialized launching gantry featuring a structural lifting capacity of 900 tons advances incrementally along the tops of the established column line. The primary hydraulic winches reach forward, suspending the precast girder high above the soil. The gantry lowers the massive concrete block onto the bearing pads. The margin for error is minimal. The placement tolerance is restricted to just a few millimeters, requiring precise hydraulic adjustments to align the load safely. Steel tendons running through the girder body receive further post-tensioning. Hydraulic jacks pull the cables with extreme mechanical force, stretching the metal before a specialized protective sealant is pumped directly into the internal ducts to prevent long-term corrosion. The elevated track advances 30 meters at a time, forming a continuous concrete deck over the Kenyan landscape. This specific viaduct design intentionally intersects the vast territory of Tsavo National Park, creating a physical separation between the heavy transport infrastructure and the natural ecosystem. By elevating the standard gauge railway on these precisely aligned concrete columns, engineers successfully eliminated surface-level environmental barriers. Migrating wildlife moves freely beneath the completed superstructure. The concrete superstructure spanning the national park stood ready, but handling heavy freight required a precise steel rolling profile. A railway rail is never cast directly into its final form. It begins as a solid, rectangular steel billet weighing several tons. Inside the metallurgical furnaces, the temperature climbs to 1200 degrees Celsius. The radiant heat from the glowing metal distorts the surrounding air. At this extreme thermal threshold, the steel loses its rigidity and becomes highly ductile. It yields. It flows under heavy pressure. The shaping process relies on sequential mechanical deformation. The incandescent block enters the primary set of rolling mills. Massive steel cylinders compress the raw material. The billet elongates slightly. With each successive pass through the reduction rollers, the cross-section changes. The mechanical pressure gradually forces the metal to form a wide, flat base for structural stability. A narrow web develops in the center to distribute vertical loads. The top section compresses into a dense, rounded head, engineered specifically to withstand the severe dynamic friction of steel wheels. Through this chronological sequence, a short, thick block stretches into a continuous rail exactly 100 meters long. This infrastructure demands rigorous specifications. For heavy freight corridors utilizing the standard 1,435 millimeter gauge, these rails must weigh exactly 60 kilograms per meter. A minor metallurgical flaw compromises the entire line. The 100-meter segments cool in a tightly controlled environment to prevent thermal warping or internal microcracking. Once the temperature stabilizes, hydraulic presses straighten the steel. Mechanical saws cut it to exact transport dimensions, and heavy gantry cranes load the finished profiles for dispatch to the Savanna assembly site. The cast concrete pillars formed the viaduct, but without fixing the steel rails with millimeter precision, this elevated structure cannot safely receive trains. A loose rail on the ground remains merely a heavy metal bar until it is anchored to the foundation below. The stability of the railway depends on rectangular concrete sleepers, which distribute the heavy dynamic load. Engineers use pre-stressed concrete to manufacture these components, ensuring they withstand the constant impact of loaded freight cars. Inside the molds, high-tensile steel cables are mechanically stretched tight before the wet concrete is poured over them. Once cured, the released cables compress the material inward, giving each block the structural density required for continuous operations. Each sleeper measures 2.5 meters in length and weighs between 250 and 300 kilograms. The design demands between 16 and 1700 sleepers for every single kilometer of track. 480 tons. With the entire line stretching 472 kilometers, the logistics require manufacturing and transporting hundreds of thousands of concrete blocks. To accelerate construction across the savanna, crews pre-assemble 15-meter modules containing between 20 and 25 sleepers at off-site facilities. Heavy lifting cranes then lower these complete sections onto the finished bridge deck for final position alignment. Every track segment must match the Stevenson International Standard Gauge of 1.435 meters. Zero tolerance for deviation. Workers then secure the steel rails directly to the dense concrete blocks using heavy-duty metal mounting clips and threaded bolts. The sections spaced at 1.435 meters remain just separate segments until molten metal fills the gaps. Crews apply thermite welding. This chemical reaction generates temperatures exceeding 2,500 degrees Celsius. It instantly melts the steel. The heat fuses adjacent rail ends into one solid mass. Repeated across the line, it forms a single continuous metal ribbon stretching for hundreds of kilometers. There are no mechanical joints. A heavy train travels across this smooth surface at full speed without producing the rhythmic clicking of the wheels. Over this continuous steel ribbon, passenger trains cover the distance from the coastal port of Mombasa to the Central Plateau in 4.5 hours. For an entire century prior, the colonial-era narrow-gauge tracks demanded more than 24 hours to complete the exact same route. The physical mechanics of regional transportation underwent a definitive and measurable shift. A modern heavy locomotive glides steadily along the elevated concrete viaducts. Below these sprawling tracks, wild herds pass safely through preserved migration corridors located between the structural pillars. Inside the new passenger cars, local travelers sit in heavily air-conditioned environments. They remain fully insulated from the intense equatorial heat and the thick red dust of the previous era. Unsealed wooden carriages are absent from the main transit line. Commercial freight operations experienced an equally drastic reduction in delivery times. Goods that previously deteriorated in slow truck convoys now reach the capital city markets on the very same day. Supply chain managers can finally predict arrival schedules without factoring in long delays caused by crumbling infrastructure. During the active construction phases, the expansive building sites required extensive manual and technical labor. The engineering project generated direct employment for tens of thousands of Kenyan workers across the entire regional route. Local technicians learned to operate complex Chinese-built locomotives and manage advanced digital signaling networks. Other local workers received specialized training to maintain heavy construction machinery and large-scale track-laying equipment. Engineering crews poured thousands of tons of concrete and assembled heavy steel segments. This continuous building process transformed isolated rural outposts into active regional transit hubs. Local commercial activity quickly accelerated as merchants adapted to the passing daily freight schedules. However, this logistical acceleration carries a severe and lasting financial weight for the national treasury. The physical construction of the modern standard gauge line required huge capital expenditures over several years. Total building costs for the primary route ultimately exceeded $3.2 billion United States dollars. To fund the large-scale infrastructure overhaul, the central government secured large foreign loans from external financial institutions. The swift transit speeds come at a steep national price. Every hour saved on the journey adds another layer to the repayment schedules extending into the coming decades. The technical efficiency of the new railway system permanently carries a multi-billion-dollar sovereign debt. This demand for speed and capacity reshaped the physical geography of Kenya. The original British colonial track is finally gone. Historically nicknamed the Lunatic Express, that narrow-gauge railway operated for over 1 century. Today, a continuous concrete viaduct cuts straight across the dry terrain. Thousands of reinforced piers lift the heavy steel rails above the plains. Builders bypass the unpredictable ground conditions entirely. The tracks run parallel to the old colonial dirt paths. The new infrastructure replaced uneven earthworks with rigid pre-stressed concrete spans. The entire route stretches directly from the coast deep into the interior. Modern passenger trains now glide smoothly along the elevated concrete structures high above the savanna.